All right, so today we're very glad to have Konstantin Aleshkin from Columbia University, and he'll talk about central charges for abelian GLSMs. And Konstantin, you can start.
Okay, thank you very much. Thanks for the invitation. It's nice to give a talk here. It's yeah, I looked at the speakers of the seminar. It looks amazing. It's a very interesting seminar. So yeah, it's nice to give a talk here. So
thank you.
The topic I'm gonna discuss today. Yeah, right. Maybe before I should say that yeah, please interrupt me because different people have different backgrounds, and so I want us to be more or less on the same page. So the topic I'm going to talk today is something I've been thinking about for a few years. It's based on joint work in progress, still with Melissa Liu. Yeah, we plan to finish it a while ago, but always there are some
so this
details.
Is like the next paper of your recent post.
Yes. So yeah, this is still not posted. So the paper which appeared in archive, I'll say a couple of words about that. It's in a certain sense generalization of this project in one direction.
I see. Okay, thank you.
So right, and this is so I call this central charges for abelian GLSMs, and basically it's so maybe I should say some plan for my talk. So first, I want just to discuss GLSMs. It's an enumerative theory and central charges. So then I'm gonna talk about what we call Higgs-Coulomb correspondence. For central charges of this object over here. And so this terminology actually came from physics, and this is slightly different from what let's say people like Nakajima and some other people have talk when they speak about, let's say, Coulomb branch, Higgs branch. But I'll also comment on that. Yeah, and then if time allows, I'll also talk about some mirror symmetry for the same objects. Mirror symmetry. So, oops. Especially since it's a mirror symmetry seminar. So, all right. So, first of all, what's a GLSM? What is a GLSM? Terminology again came from physics, so it's called gauge linear sigma model. Gauged linear sigma model. And yeah, originally it was formulated by Witten I think in the early 90s in the physical context for studying very similar things. So and the terminology is actually very simple. So sigma means that we're studying maps of curves. Linear means that we're studying maps to a linear space, that is to a vector space. So it's doesn't sound very interesting. And gauged meaning that we're actually studying maps model some equivalence. So we have some gauge group, and that's what makes this business interesting. So maybe first I want to recall a GIT data and the associated enumerative theory. So a simpler theory is a theory of quasi-maps. Yeah, maybe I should make some citations. So written around the early 90s, it's a physical formulation, and then mathematical formulation was done by Fan, Jarvis, and Rowan. And then yeah, I'll mostly use constructions from Fan, Jarvis, and Rowan, and a recent paper by Fiver and Kim about constructing cohomological field theory based on this GLSM. But there are, of course, other works. So a simpler theory is a theory of quasi-maps. and which was started again in the almost not 20 years ago, but 15 years ago by Mellin and Konstantin. So a quasi-map is some generalization of a stable map. And the idea is that if we have a GIT quotient, so let V be a finite dimensional vector space. And G, we say G is a subgroup of GLV, a complex reductive group. So then if we take some character of G, so let omega be in the characters of G. It can be a rational character, it doesn't really matter. So then the GIT quotient of V mod G, so then we call GIT quotient, we call it X omega. And yeah, there are a few different notations. So it's V, I use notation V double slash sub omega G. So this is basically sorry, let me organize my screen a little better. So it's some subset of V defined by omega. So omega semi-stable locus quotient by G. And I think about this object as a, so the brackets mean that it in general, the semi-stable locus, the action of G on the semi-stable locus can be still unfree. And so this can be a dilemma for stack. So in general, this is a smooth, not necessarily smooth, so it's a dilemma for stack. And today all the spaces will be smooth. And so what's a quasi-map? So a quasi-map from an Norby curve curly C, maybe with some marked points. Let's call them, vector of points to X omega is actually a map to the, so is a map from C to the stack quotient, so to the Artin stack of V mod G without any stability conditions, which generically maps to the stable locus. So to the omega semi-stable locus. And there are of course notions of automorphisms, there are notions of stability conditions, there are notions of stable quasi-maps, but so for now this is just a general idea of what quasi-map is. You yeah, probably most of you know what it is. And a GLSM is a certain generalization of a quasi-map. So GLSM data is a 5-tuple V, which is the same vector space as in JT data, G, same group, then C star, which I denote C star sub R, endowed, so it's an additional copy of C star with an action on V, W, this is called superpotential, and omega. Omega is a stability parameter. So V, G, and omega are basically the quasi-map data. So that is the data of JT quotient. So V, G, omega is a JT data. And so we have two additional objects, C star R and W. And C star R also acts on V. So think about it as a subgroup of GLV that commutes with G and has a finite intersection. So its intersection is a finite group, and well, since it's a finite subgroup of C star, then it's just some group of roots of unity. So it's mu R. It's a group of R's roots of unity. So this is what I wanted to say about this C star. Right. So this C star action on V is called R charge action, and weights of this action on V are called R charges correspondingly.
Sorry, Konstantin. We cannot hear. Can everyone hear? Something wrong with the. Can you hear me?
Yeah, I can hear you now.
Okay. Now it comes back.
Oh yeah.
So maybe.
Sorry.
Yeah.
Apologize. Something happened with my earphones apparently.
Yeah. Okay. So I think we stopped at this W is a superpotential.
Right.
Can you please go back a little bit? Yeah. Thank you.
Sure. Right. So this C star R is called R charge action, and W is a holomorphic function on V, which is G invariant. So it descends to the JT quotient X omega, and it's covariant with respect to C star R, so it has weight R with respect to this action. It's like a weighted homogeneous polynomial. If all the C star weights are positive, that is. So conceptually,
Sorry, can you give us an example that you have in mind about this? Just like
yeah, exactly.
the most typical example of this.
Sure. Yeah. Example. Yeah, maybe my favorite example. It's a bit simple, but it's fine. So it's V is C5 with coordinates X plus C with coordinate P. Our group G is just C star with weights. So C star acts on this C6 with coordinates, sorry, with weights 1, 1, 1, 1, 1, negative 5. Then C star R acts on V with weights 0, 0, 0, 0, 0, 1. So weight 0 here, weight 1 here. Superpotential is going to be P times a quintic polynomial of X. So I wrote Fermat quintic, but it doesn't have to be Fermat quintic. As usual in enumerative theories, this theory is also a deformation invariant. So and then so stability parameter omega is in characters of a torus, and characters of a torus is just integers, and we want it to be non-degenerate, so it's basically either positive or negative. And let's see what's going on in this case. So in this case, if omega is positive, then x omega is, so it's a quotient of this v by c star when we remove some unstable locus, and the unstable locus in this case turns out to be the origin in C5. So it's C5 minus the origin cross C, quotient C star. And so the weights are 1 on these 5 coordinates and -5 on this coordinate. So when we take the quotient, the first factor produces a copy of P4, a 4-dimensional projective space. And then this last copy of C, it produces a line bundle of -5 over P4. So in total, this is KP4, which is a total space of -5 over P4. Now, so what is the role of this idea? This is a JT quotient. What is the role of W and C star R? So conceptually, yeah, first of all, you can see that this potential is invariant with respect to G because P has weight -5, polynomial of degree 5 has weight 5 under this action. And then it has R charge 1. So only P has weight, and this weight is 1. So conceptually, GLSM is a theory of a critical locus of W inside X omega. So let's compute the critical locus of W. So critical locus is locus where the differential vanishes. So differential is dp times the polynomial plus p times differential of the polynomial. It must be 0. So well, dp is never 0, so it implies that the quintic polynomial is 0, and this differential form is 0 only when all the xi's are 0, and all the xi's are 0 is the unstable locus. So it never happens on X omega, so P also must be equal to 0. So P is equal to 0 is a 0 section of the canonical bundle. And of course, this is a quintic polynomial, so critical locus of W is just a quintic inside P4 embedded as a 0 section into KP4. So in this case, GLSM corresponds to the Gromov-Witten theory of the quintic in P4. So now you could ask, what's going on for the other choice of stability condition? So now if omega is negative, so this was one choice of a character, a positive choice. For the negative choice, the stable locus is different. So x, let's call this x minus, let's call this x plus. It's for positive omega, for negative omega. X minus is going to be what? X minus is going to be C5 cross C minus the origin. So now the unstable locus is 0 inside the other component. And this whole thing quotient with respect to C star. Now the action is not free, actually. So we have to take the static quotient. And now we can use the C star to actually to fix this point in C minus the origin, which is also the morphic to C star, to be equal to 1. But since the weight of this action is -5, there is a residual symmetry, so which acts diagonal on C5 by 5th roots of unity. So the result is just a C5 mod mu5, where again mu5 is a group of 5th roots of unity, and the action is diagonal. And it's easy to see that the critical locus of W is just the origin. So it's the origin, it's an orbifold point, so think about it as a stack, as a dilemma for stack, 0.5. And so for negative character stability condition for omega negative, GLSM computes FJRW theory of the pair C5 mod mu5 and W. So now you see how basically we have the same GLSM where you can change the stability parameter, which changes the GID quotient and the corresponding theory. And thus this theory is very convenient to study wall crossings of this type. So in particular, there is a correspondence between these two GLSMs, x plus x minus with these potentials. And so there is a correspondence between Gromov-Witten theory of the quintic on one side and FJRW theory of this pair on the other side. So this is called, this correspondence is called Landau-Ginzburg Calabi-Yau correspondence. It was studied by many people, Kyoda, Iwatani, Rowan, Jiang, and others. Yeah, British Shoemaker. And again, the list is not full by any means. And it's called Landau-Ginzburg Calabi-Yau correspondence because of FJRW theory is called also Landau-Ginzburg theory of this pair. And well, quintic is a Calabi-Yau threefold. So more interesting example, but a very similar spirit. Sorry. Is a mirror quintic. Well, in this case, our vector space is also C5 with coordinates x, but the second summand is actually C101 with coordinates p, because H2 of the mirror quintic is 101 dimensional. And the gauge group G is also 101 dimensional. It's C star power 101. So the action of G on V is given by some 101 by 106 matrix, whose coefficients can be read off the mirror potential, which is, well, mirror to the mirror quintic, which is equation of the usual quintic. So it's actually, even though it looks sorry, give me a second. I think something is wrong with my earphones. I'll try to switch to the other source.
Yes, please. It stopped like for a few seconds.
Can you hear me now?
Yes, it's good.
Okay, yeah. Sorry for that. Okay.
It works now. Very, very nice.
All right. So the more interesting example is the mirror quintic again, where the dimension of both V and G is much, much higher. but the data is quite simple. So it's given by, again, by the data of the polynomial of the quintic. And then, yeah, so you can also write some superpotential, which will be, yeah, in the general quintic form, but there will be a lot of these coordinates. So SAI is 101 times 5 matrix. Clarify. But what's important is that the stability parameter omega is a character of G, which is now a 101-dimensional lattice. And so the structure of the stability chambers, as we call them, is much more complicated. So in particular, yeah, let me draw a 101-dimensional space on a 2-dimensional board. So this is the 101. And we would have analogs of omega minus and omega plus. So, and this will be a Landau-Ginzburg phase, where x omega is going to be, x minus is going to be C5 modulo mu5 power 4. So it was C5 modulo mu5. And in the mirror quintic case, we have the orbifold group that x on C5 is bigger. And in the other phase, we will have x plus is going to be Kp4 modulo mu5 cubed. This is also not a secret. This has been known at least for 30 years since works of Candelas and his collaborators. But now there are much more phases and structures inside this space. So with Melissa, we studied some other chambers which are adjacent to this chamber omega minus. We'll have 101 hybrid, so-called hybrid phases, which has not been studied, I think, before, because if you don't think about it in terms of GLSM, they don't correspond to neither some Gromov-Witten theory of some space nor a singularity theory of some function. And also there is a big question mark here because there are many phases which we haven't studied, but which can be studied somehow all at once by considering GLSMs with different stability conditions.
So these lines are chambers for stability conditions.
Exactly.
So they will change for. So are you? How many lines are there?
So in principle, this is 101-dimensional space, and there are a lot of chambers, and I don't know how many there are for the mirror quintic.
But that part is not studied.
Yes.
And for this 101 hybrid phases, what kind of theory is it?
So it's some new theory. It's some curve counting theory, which is, I mean, it is a GLSM in this sense. It's not new, but it doesn't correspond to any other known theory as far as I understand.
Okay, I see. Thank you.
And in fact, for many of the there are some certain subclasses which I might discuss later as well. Right, but these 3 examples, they had like a common theme, which is actually a generality we worked in this paper. So we consider abelian Calabi-Yau GLSMs. Well, abelian is easy. It's when G is an abelian group, so G is some torus. And then X omega is actually a toric Gilliam-Upper stack. Is a semi-projective toric Gilliam stack. And Calabi-Yau means that X omega is Calabi-Yau. So GLSMs are obviously defined for more general setting, and we believe that all the methods that we use can be generalized to in both of these directions. But yeah, I'll talk about them when I'll explain what is the curve counting corresponding to this. But any questions before? All right. So now, what is a GLSM map? That they called Landau-Ginzburg quasi-maps. And so remember that a quasi-map was a map to the Artin stack V mod G. And so for GLSM, we actually start with a similar map, V mod gamma, where what's gamma? So gamma is a span, or rather a group, a subgroup of GLV, generated by both G and C star R. Generated by G and C star R. So this is our LG quasi map. And then there is a compatibility condition. So what's the compatibility condition? So because in this map V mod gamma, there is no superpotential involved. So first we can project it to just a point mod gamma, which is just B gamma. So well, if this, so what was this map? So map from a C to a B gamma is just a principal gamma bundle, which I also denote P. So this level is a principal gamma bundle P over C. And F can be thought, so what's F? F is a section, can be thought of as a section of an associated vector bundle with a fiber V. So, and the compatibility condition is that, well, we can further construct a line bundle out of this principal bundle, which I'll explain in a second. This line bundle must be the log canonical bundle of our curve. So what's C star W? Well, we have an exact sequence of groups. And so we can define a quotient of gamma by G, and this quotient is C star omega. And in fact, this quotient is just a finite cover of, a quotient of C star R. No, a cover of C star. So remember that gamma is a group generated by G and C star R, and they have finite intersections. So this is a quotient.
Sorry, what's that small r up 1 over r there?
Oh, it's just a R's cover of, so it's 1 over R. It's R's finite cover of C star R, which I write just.
And r is any integer?
R is the order of our GLSM, so it's
Order.
intersection of G and C star R was a group of roots of unity, and we called R the order of this group.
Okay. Okay.
All right. And so this is what's called an LG quasi-map. Right. So it's also generically should map to a stable locus. And there is a notion of isomorphism of such maps, but I won't discuss this in details. What I want to do is to illustrate what's the modular space of the thing. So today, our curve is going to be, our orbit curve is going to be just a orbit P1. So it's a teardrop with an orbital point of order order A at infinity. So it's a point more than A. And then a non-orbital point at 0. And we consider with one marked point which will be the orbital point, possibly orbital point. So now what's modular space of LG quasi-maps? So since F, such an LG quasi-map, is a section of the associated bundle, we can define define quantum version of V, which is called curly V, which is just our gamma of this bundle, PV. And so the loop space, which is same as a given loop space, is H0 of this V mod G. So let me explain what's going on in the quintic example. Well, for the quintic, our group G is just C star. R is actually 1, so gamma is just C star cross C star R. So it's a quintic. Well, then what's the principal bundle over C? So our C is just an orbit P1. So any bundle is just decomposed into so it's a copy of it's a product of two C star bundles, and C star principal bundles are the same as line bundles, and line bundles over P1 are all classified by their degree. So this is let me call this OD star. So this star means that we subtract the 0 section since it's a principal bundle. Cross O1 star over U1. So this one is actually it's negative 1. Is because the log canonical. So what's log canonical of U1? So since our marked point is the orbital point, when we subtract the orbital point, we just end up with a P1 without one marked point. So log canonical is just log minus 1. So now what's an element in H0F? Sorry, what's even before? What's an associated V bundle? So this is just so let's see. Our vector space V has weights 1 and -5 with respect to the action of the first C star, which is G, and weights 0 and 1 with respect to the second. So what we end up with is we get 5 copies of O of D, right? Plus O of negative 5D. So this negative 5 is a weight of C star action on the last coordinate, minus 1, where this minus 1 is, this minus 1 comes from here, because the weight, the R charge of the last coordinate is 1. So, well, what's H0 of this? Okay. Well, for positive D, it's just gonna be H0 of 95. And this is just C 5D plus 5. So now the loop space, and the loop space, so this is the space of section. This is basically a space of sections of the bundle associated to our quasi-maps. So the loop space is basically a modular space of quasi-maps. In this example, is just a GIT quotient with respect to our group G, which is a star, which is nothing but P power 5D plus 4. So quasi-map modular spaces are usually much simpler than stable map modular spaces, because what's going on is, so you think about this space before the quotient is a 5-tuple of sections of so 5-tuple of degree D homogeneous polynomials on P1. And when these polynomials vanish at the same point, then the corresponding quasi-map at this point is not, sorry, the image of the quasi-map at this point is not stable, because it maps to the point 0, 0, 0, 0, 0 at P4, which is an unstable point. So if you want to construct a modular space of stable maps, then you have to start with this guy and then blow it up at all the loci where our image of the quasi-map is unstable. All right. So, but this space, this other space didn't enter the construction. So it enters the construction of the abstraction bundle. So we have, yeah, let's call that, sorry. Let me call this loop space as XD, where D stands for the degree of our quasi-map. And degree of quasi-map is just degree of the associated principal bundle. So then we have an abstraction bundle over our loop space, which is, well, H1 of V plus H0 of V quotient G. So this defines some perfect abstraction theory. Oh, sorry. So this defines perfect abstraction theory on the loop space. And therefore, we can compute some intersection numbers. So in particular, yeah, maybe I should speed up a little bit. So using this abstraction theory, we define the I function, given to I function. So yeah, let me write a formula and then explain it a little bit. So here I put parentheses because yeah, maybe I should put parentheses in here. So, and the image is going to be in the relative cohomology. So, relative orbifold cohomology. Of x omega with respect to the locus where the real part of the superpotential is larger than some big positive number. And of course, as a power series in the y variable, which is should be understood as logic free. So, right, I put a lot of details under the carpet here. So in particular, we define it using equivariant localization, because actually, so we define it using a localization with respect to another copy of C star, which basically rotates our P1. So with respect to, which is the given loop variable. So we have our P1, VA1, which I draw as a teardrop. And then we have an additional C star action, which equals C star Q, that rotates our P1. All right. So now what's a central charge? Now a central charge and again, terminology originally came from physics, and in mathematics, I think it was defined by Hosanna. And so we define some analogous construction for the GLSM case. So let B be a matrix factorization of W. So it's some direct category matrix factorizations. Then its central charge is a pairing of the I function multiplied by some gamma class, which is an explicit cohomology class, with a Chern character of B. And this is a pairing on this relative cohomology space. So let's call it H. It's a pairing of H. So gamma is a tiny gamma class.
Wait, so the Chern character lives in H?
Right. So the Chern, there is a certain version of Chern character for matrix factorizations. Actually, there are a few constructions by Polishuk-Weintraub, then by Kim and some other collaborators, and yeah, they map to the relative cohomology.
Well, I thought, for example, in Polystruct, it maps to the Hochschild homology of matrix factorizations.
Exactly. And Hochschild homology are naturally identified with relative homology.
Under the HKR map?
Mm-hmm. Yes. Exactly.
Without the gamma class.
Mm-hmm. So right. So this is just the chain character without gamma class, and then we multiply by. So actually, the trick we use to compute it is actually that it's so there is a tautological map from relative homology to the usual homology when we take a relative homology class and think about it as usual homology class. And so this pairing we can take our I function and then just map it to the usual homology of the underlying GIT quotient. And then this pairing is going to be equal to the usual Euler pairing on the just orbital homology of X. And this beta twiddle is actually an element of the K theory of X, which is constructed as follows. So we take matrix factorization. Matrix factorization is a data of vector spaces with maps. And then we map it to a K theory class, just class of E0 minus class of 0. So even though this is defined on the level of matrix factorization in relative homology, in fact, the computation factors through the computations on the underlying GIT quotient, which is basically the same computation as for, in our case, for toric DM stacks. Right. So now in the remaining 5 minutes, I wanted to say about our main results, basically, and about why we want to work with these central charges. That so theorem, it's formally theory in progress because the paper is not yet archived. But it should be archived in this year. So beta is a convergent power series in Y, which is equal to for some region of Y what we call a hemisphere partition function, following Hori and Roma. Okay, I'm write later. with enumerative form, and then I'll explain what I mean. Where sigma is a variable. So this is an integral over some cycle in the complex Lie algebra of G. So sigma is in the complex Lie algebra of G, which is in our case is some vector space. I mean, there's always a vector space. Now gamma sigma is an explicit function, which can be thought of as a function on G, which can be thought of as some element is in completion of cohomology of V mod G. Now, so theta is omega plus 2 pi I b. So this is inequality under identifications. Y is equal, y on the side of the central charges is equal to the exponential of negative theta, z equal to so this Chang character is defined additively, so this is Chang B on the right hand side is also an explicit function. Of sigma. So let me say a couple of comments about this theorem. So the I functions and the central charges are known. I mean, they're defined as formal power series of enumerative invariants, and it's been known for a long time that in general these objects, for Fano varieties and for Calabi-Yau varieties, they define some convergent power series. And what we did is basically we found a representation of the central charges in terms of very simple multidimensional complex integrals. So this formula is also, so it's motivated by some formula from early 10th by Hori and Roma on hemisphere partition function. And this formula is what's called localization of the Coulomb range. So this is called Coulomb range. And computation of the central charge in well, not in that exact paper, but in some other paper called Higgs branch computation. And so we call this theorem a Higgs-Coulomb correspondence, which say that the central charges of GLSMs have very simple multidimensional integral representations, in particular their analytic functions. And there are two more comments which I want to make before stopping. So first comment is, since it's an analytic function, we can do analytic continuations. In particular, we can power expand into different regions. And in the same paper, we showed that if you take two adjacent stability chambers of a single H-linear sigma model, then central charges in these chambers are related by analytic continuation. Well, but now you need to say something about the matrix factorizations. Well, and so the central charges of two matrix factorizations are related by analytic continuation, if and only if these matrix factorizations are obtained as Fourier Mukai transforms of each other. So this is compatible with on the nose with the great restrictional and Fourier Mukai transform. Yeah, maybe a couple other words. Sorry. So second comment is that. So we did this for abelian Calabi-Yau, general abelian Calabi-Yau GLSMs. So for non-abelian GLSMs, we believe that our methods will generalize, even though the computations will be less explicit. For non-Calabi-Yau GLSMs, though, we need to modify our tools because the analytic properties of the central charges in the non-Calabi-Yau case will be more complicated. So instead of some convergent power series, we'll still have some integrals, but instead of convergent power series, we'll have to identify the asymptotic expansions. And the last remark is that these integrals, they have a nice representation in the quantum K-theory. And so our paper with Melissa and Archive that appeared last week is about actual generalizations of this story to the K-theory, where in the K-theory, the analogous Coulomb branch integral representation has a meaning of a central charge of maps of formal disks into the quotient image. Okay, yes, sorry for being over time. I'll stop here.
Okay, thank you for the talk. And so are there any questions? I think we have a few experts. Maybe they here. I think Emmanuel and Zhengyi. Well, I have a question. So, so you call this central charge. Do you know it's related to stability, regional stability on the?
So this is right. Yeah, thank you. So this is. Yeah, I'm not by any means an expert on regional stability conditions, but in my understanding, this relates to the central regional stability conditions in the same way as Hosan's central charges do. That is, I think, so you can use these central charges. So this, in particular, via mirror symmetry, they correspond to period integrals. So this is something. Yeah, sorry, I didn't have time to talk about this. So by the mirror symmetry, they correspond to some oscillating integrals of mirror LG models. And so you can construct, I believe you can construct regional stability conditions out of this central charges.
So this is not known, right? Or is it known?
For GLSMs, I think it's not known, but in some cases, yeah, I cannot say the precise statement, but I think it was as a folklore, at least as a folklore, there should be a relation. Maybe Yukinobu is like one of the best persons to ask to know this.
Okay.
But I would say, okay, so maybe one final remark that actually our central charges are quasi-map central charges. So in the literature, mostly when people say about central charges, they consider stable maps. So I think stable maps, central charges, and quasi-map central charges are related by the mirror map. So I think, yeah, what I said should be, yeah.
Also, in the case of stability, they also have this chamber. It seems the same as what you are picking as a polarization, right? This omega that you're saying. And there's this this wall crossing formula for DT invariant. And here you have your invariant. And do you know how they transform under this transition?
Right, so those are different stability conditions actually, because and the different whole crossings. There are a lot of whole crossings in the literature. So the stability conditions which we discussed are not Bridge stability conditions, even though I believe that the central charges are related with Bridge central charge. So the stability conditions that I've been talking about these are just JT stability conditions.
That's right. That's right.
Well,
but I was wondering if you have a similar kind of transition. Do you know how they relate? Right, that's my question. How the invariants depend on when you cross a wall? How do they transform?
Yeah, exactly. So at least under our stability condition, we know exactly how it happens. And this is precisely because of this integral formula. So if you cross a wall, you just take analytic continuation in your variable theta, whose real part is identified with the stability condition omega. And then you take a Fourier-Mukai transform of the insertion B.
I see. So you have something global actually here.
Exactly. So the advantage of this Coulomb branch integral is that it gives a global object for a GLSM which doesn't depend, which is defined for all stability conditions. And as I said, for quantum K theory, there is an analogous object, and there it has more direct interpretation in terms of enumerating of maps of formal disks into just V mod G without, and it's an Artin stack quotient without any stability conditions.
I see. All right. Are there other questions from the audience? Okay, so if there are no further questions, let's thank Konstantin again. Thank you. Thank you for the time. All right, so that's it for today's talk. Thank you very much for giving the talk.
Yeah, thanks again for the invitation.
It's very, very interesting.
Have a nice day. Bye.
Okay, bye. Bye, everyone.